Okay, hello, welcome to today's webinar, Creating Impactful Virtual Shopping Experiences Using Artificial Intelligence and Computer Vision. This is part of our Customer Speak series of webinar, and today's webinar is hosted by Trigent Software. Trigent is a leading IT outsourcing and offshore software services provider. We provide consistent, reliable, and superior technology services across the industries. Our digital transformation services include IoT, cloud, artificial intelligence, DevOps, and software QA. We differentiate ourselves with custom solutions to business problems, attention, care, and flexibility that we provide to our employees and customers. Our technology strength is evidenced by multiple patents. We have won several awards in the recent past, including the North American Software Testing Award, Zinnov Zone's Engineering R&D Award, and Insight Success 10 Most Admired Company to Watch. Before we get started, few housekeeping announcements. As a participant, you will be muted. The expected duration of this webinar is about 1 hour and 15 minutes, and we will have about 10 to 15 minutes at the end for question and answers. If you have questions, you can ask them anytime during the broadcast or anytime during this webinar. There is a question pane in your control panel. You can expand that and then type your question in and send that. We would have few polls during this webinar. Please participate and let us know what you think. This is a great opportunity for us to solicit feedback and hear from your opinions. And lastly, this webinar will be recorded and made available at a later date. Here are our speakers today. Kumar is a seasoned executive with expertise in product development and digital transformation. Kumar leads the technology division at Atrix, overseeing the industry-altering food scanning technology and integrations. Previously, he was an executive director for Verizon. Kumar holds a PhD in computer science from the University of Central Florida and an MBA from the Wharton School of UPenn. Welcome, Dr. Kumar.
Thank you.
And I'm very happy to also have Dr. Anthony Ezzi. He holds the position of Julian Hightower Chair Professor within the School of Electrical and Computer Engineering at Georgia Institute of Technology. He also directs the Laboratory for Computational Computer Vision at Georgia Tech. He has 25 years of research experience in shape optimization via geometric partial differential questions. Glad to have you, Professor Ezzi.
Thank you.
And now over to you, Kumar.
Thank you. Let me share my screen.
Sure.
Is that good?
Yes, it is.
Okay. Thank you. Thanks, Stella, for the very kind introduction. So we will talk about this topic here, and in terms of the agenda, we will quickly go through the latest AICV trends and the impact of the pandemic, and specifically we'll go through a use case that is relevant to the furnishings industry. Anybody that sells clothes or footwear, there's an opportunity to use AICV to create a personalized customer journey. We will kind of go into some detail on that. And in that context, we will discuss some technology and platform choices and some of the best practices. And before we get started, we thought it would be a good idea to have a poll in terms of the general feeling among this audience about the impact of the pandemic on AICV. So I will pause for a moment to have Chella pose that question.
Yes, Kumar, we're launching a poll. We're waiting for people to answer. You give another 20 seconds for people to answer. Great. Kumar, 8% of people said they are substantially invested in the AI/CV area. The remaining about 45 and 38% say yes, somewhat, and no, they've never been. They've not increased their investment. So that's careful. But it looks like majority of them are spending money on AI/CV now.
I mean, that is somewhat expected. As you can see from the charts here, even before the pandemic, you would see that the private investment in artificial intelligence had been increasing, had been on the way up. We are all very familiar with some use cases, right? Like self-driving cars, autonomous driving, cancer drug development, even the vaccine that was developed last year. We are told that AI played a big role in that development. And facial recognition that we all uses computer vision that the professor is going to talk about in a moment. And 3% of all the papers published in the scientific community has been on AI/CV related to artificial intelligence. And The Economist, in the middle of the pandemic last year, published that Technology Quarterly, which was focused solely on artificial intelligence. And the projection there was, in the next 10 years, AI would pretty much double the world's economy. It's a huge deal. And some quick definitions here: computer vision is using computer cameras to identify and analyze objects, just like our human eyes do. Machine learning is computer programs that learn from experience. Deep learning is a special part of machine learning, which is becoming more and more popular in this field. And it basically mimics the way our brains and the neurons work in our brain. Natural language processing, chatbots, and robotic process automation. I'm sure this audience is very familiar with them. We will touch upon them. We will mainly focus on the first three areas that are shown on the slide. In terms of the software trends in the field of AI, the one area that has been trending up very much is the software platforms area. As you can understand, AI at the end of the day is still at the beginning of its long journey, right? And you need a lot of plumbing and a lot of underlying platform support in order for data scientists and artificial intelligence researchers to do their work, and that's where most of the growth is. And you can also notice that application development and deployment, like the use case that we're going to talk about today, is not very far behind. And in general, these are the areas that are leading the growth. What are some of the top AI topics that we are talking about this year and we'll be talking about in the coming years? The first thing to note is, as we can all see around us, right? Cloud is the primary platform for AI. Even if people are not using the cloud for specialized software, they are using it at least to store that data, because the data requirements for AI are really huge. AI ops is another area that's helping IT folks automate their jobs to speed up issue resolution and drive down mean time to repair. Chatbots are assisting humans at contact centers. Increasingly, especially during this COVID crisis, people are working from home. So chatbots have really ramped up in terms of the development. RPA, robotic process automation, is automating repeated tasks to augment the increasingly remote workforce. All of these things actually require the data to be structured. But in the business world, the data as it comes is usually in an unstructured form. So AI is also being used to structure that data. And given all of this progress, right, the trends that we can expect to happen in the near future is AI, artificial intelligence itself, will become more explainable and more understood by people. The talent will remain tight because of demand. and the impact on human labor itself will be debated. And to this on this point, I just want to have an interesting poll question asked here. So Chela, if you can roll the second poll.
Sure. I launched the second poll. The question is that the first bank ATM was introduced in 1969 in New York City. 50 years on, how do you think that this has impacted human bank teller jobs? Please encourage all our participants to answer the question and kind of let us know what they think. It's your opinion that definitely matters. Please let us know. About half of our participants, a little over 60% has voted. I'll encourage others to vote also, please.
Great.
Okay, I think we got majority of the responses in. Kumar, the majority of the people, that is 63% of the people, say the ATM has mostly replaced human tellers, and the remaining are split across 13% saying the ATMs have reduced human teller position somewhat, and 12% of the people think the number of human teller jobs have remained the same, and about 18% think that the human teller jobs are actually grown. So most people ATMs are replaced.
Thank you, Chela. The 18% would be right. It's kind of hard to believe, right, that we would all think 50 years on, it should have had some impact on human teller jobs. Actually, the truth is the number of human teller jobs that we have today is more than what we had back 50 years back. So I don't think this question is answer for this question is settled for at all. It's going to be watched very closely, and we'll all understand how this works. But at least so far, the evidence has been that no, AI is actually augmenting the workforce, but it's not really replacing them. So I just wanted to, I thought, it would be interesting tidbit for us all to know.
Very interesting.
And let's, with that kind of a background, let's talk about this specific opportunity that we are here. Tony and I are here to discuss. This is an artificial intelligence / computer vision opportunity that is specific somewhat to the furnishings industry. Anybody that sells clothes or footwear. Let me ask you a question. How many of you have in the past several months have had to return a product because it did not fit? It is not a poll question because we think we know the answer. Probably close to 100%, right? All of us do that, especially when we are increasingly shopping on the e-commerce platform. It's products just don't fit. The advertised sizes of the products don't seem to make us feel comfortable in them, so we return them. And that is a huge problem for the retailers. And CNBC says it's $1 trillion problem. And I know specifically in the shoe industry, 25 to 30% of the shoes that are purchased are actually getting returned, and it's a big cost issue for the retailers, and a lot of them do not even understand that space thoroughly. It's a big opportunity. And what we are proposing here is that there is a way for AI CV to play a role where you can use computer vision technologies that the professor is going to talk about in a moment to measure the body accurately, whether you're measuring your foot or you're measuring your body for clothing. You can use some of those technologies to measure them accurately, but then just good measurements is probably not going to cut it, right? Because we all know we have a fit preference that is aside from the actual measurements that we get. Some of us like to wear things loose, some of us like to wear things somewhat more snugly, and so forth. So it would be important for us to get those measurements accurately, but also superimpose on them the actual preferences of customers, either by asking them some questions about their purchase behavior, or actually looking into the purchases that they make, because which is where they put their money where the mouth is, right? And use some deep learning, machine learning models to actually make predictions, very accurate predictions on the right products to recommend to customers. And the goal of this is to improve the customer lifetime value. And this is what the journey would roughly look like, right? You have the brick and mortar presence of the retailer on the left-hand side. They can have a specialized scanner if they want to measure the customers, and it can also be done on a mobile device in a home setting. But as we will argue on this in this discussion, we believe the technology for measuring the body accurately, where the measurement accuracy is expected to be within a couple of millimeters, it's not there, just because technology is not ready. So increasingly, shop owners, retailers are actually using sophisticated scanners, specialized scanners, to bring customers in, measure them, and then that information is actually fed to a machine learning database, where the customers' actual purchases, the purchases that they make after they are done measuring, and their preferences that they express are kind of combined, and some machine learning models are trained. And the end result is, when the customer goes to their e-commerce channel in the future, they have very, very tailored products recommended for them on the e-commerce channel. It's like a lifetime value improvement proposition for the retailers. And so with that said, there are a couple of technologies that we will discuss specifically. One is the computer vision area, where you would start with some kind of a 3D reconstruction of the body and measure the dimensions out of it. Like we said, either using a special purpose scanner or a mobile device at home. And then you kind of feed this data to a centralized machine learning database, and you train some models based on customer purchase behavior and their sizes. And we will talk about that in the second topic. So what I will do right now is I will turn it over to the professor, and I will pick it up on the other side of computer vision to talk about these deep learning models. And before I turn it over to the professor, a couple of words about him. I have known Tony, probably for a couple of years, Tony. And he has been consulting with Atrix and has been helping us hugely with some of the work that he's going to talk about in computer vision. And he's probably the foremost expert in the world when it comes to using partial differential equations, as he would explain, for 3D reconstruction. And it works very well for objects that are somewhat textureless, like human skin. And it's been an honor for me to co-host this with the professor. And without further ado, let me turn it over to you, Tony.
Thank you very much, Kumar. Okay, does everybody hear me okay? Okay, yes, and hopefully everybody sees my screen. So let me go ahead and okay, everybody sees the slides okay now?
Yes.
Okay, great. All right, so let me just move this control panel out of the way here. Okay, so let me talk a little bit about 3D reconstruction using computer vision. And I'll be a little bit more specific about it, that it's there are many methods for doing 3D reconstruction, and there are several commercial products also for doing 3D reconstruction. And what you'll find is most of them, in fact, all of the ones that I'm aware of commercially are based on point cloud generation. And some also are based still based on point cloud generation, but combined with artificial intelligence to try to generate objects of known types. And I'm going to talk a little bit about that towards the end here. But what I'd like to do is introduce another form of 3D reconstruction that actually was of a lot of interest in early years of computer vision, and I'm talking about the 90s and the early 2000s. It's a little bit more computationally intensive, but with modern day computing, it's actually now become practical. And they're techniques that are based on solving partial differential equations. So they're intimately connected to things from physics, both computationally as well as from a modeling standpoint. And one of the early ways that people used partial differential equations it was more in image processing rather than computer vision, was to try to do denoising. So you can think of heat diffusion and the way the temperatures of objects that are unevenly heated will cool naturally if you just allow them to do so without any outside influence. And things in the diffusion effect has a smoothing property, and people applied those to images, found that they worked very well, and then realized that they could play with these diffusion equations, these partial differential equations, in more non-physical ways to attain certain effects, such as how do I denoise an image while preserving an edge, or how do I measure motion fields in an image, where I know there's discontinuities between overlapping objects, right? So it began a whole field of using partial differential equations that were custom tailored to solve problems in computer vision. And while I would say that the vast majority of modern day computer vision is based on machine learning, this more variational PDE-based approach to computer vision is still going on today. In fact, there's an entire conference dedicated to it that occurs every 2 years. So I'm going to talk a little bit about that. But let's just touch on the more traditional approach, I don't want to say the more traditional approach, the more popular approach modern day, which is the use of point clouds. And so the typical approach that you'll see in commercial products is that you either do a scanner, which gives you directly a set of points in 3D space, or there are now computer vision based stereo cameras that will generate point clouds for you. There's devices such as the Connect device that generates the point clouds for you. But anyway, so one approach is you generate point clouds. Now, how do you do that from images? The way that you typically do that from images is that you look for features that are easily distinguishable and identifiable from two different points of view. So if I take a picture, for example, of a person wearing a plaid shirt, you'll see all of the corners of the marking. Or if you take a picture of a scene, and then you can find corner features, for example, of a building. Then you can match those from image to image. You can triangulate them back to the camera positions, see where those rays intersect in 3D space, and you get a point. Now, if you do that for many points, you can generate a cloud, and you can try to interpolate that and get a 3D measurement. So what you see on the top here is a point cloud, a reconstruction of a foot. And that's one of the products that I'm working specifically with Atrix on, is trying to do a 3D reconstruction of the anatomy of the foot. And what you see on the bottom is a point cloud that's generated directly by a modern stereo depth cameras. And that's the way that they do it. They identify textured features of interest. If there's not a lot of texture in the scene, then a lot of cameras will actually project on using infrared lights, complex patterns, so that they can generate feature points from which they can do matching and triangulation and generate a point cloud. Okay, so this is what's common today. Now, one of the drawbacks of this is that you'll often have some noisy outlier measurements, and you can actually see that in the images below. You can see that there's kind of in the backgrounds, in the middle of the top of the right image, and in the middle of the bottom of the left image, you see artifacts. And typically those come from false feature matchings, that that the feature detected in one image isn't properly matched to the feature in the other image. And then you also see missing measurements where there really wasn't any feature of interest, even when there's projected patterns. So now let me talk a little bit about another approach We call this point cloud generation approach a bottom-up approach, because we're finding local features of interest in the image, and then we try to match them, and from that we compute geometry, and that's the traditional solution. If I give you an image like these, though, so these are some salt and pepper shakers, which were chosen as objects that don't have a lot of obvious point features, and we put them on a highly textured background. So you see this kind of wallpaper that we chose that has point features all over the place, which makes the feature matching problem extremely challenging. So this becomes a more complicated problem to address using, point cloud-based approaches. So what would be a nice solution is images like this, precisely because of the either the even distribution of features as you see in the background, or the lack of features that you see in the foreground, are typically regions that are easy to segment. They're easy to differentiate regions, like foreground from background, because there's some level of contrast that you can exploit. So what I'm going to show you, and this is the basis of some of the methods that we're using together with Atrix, is an approach that we call it a top-down approach. So instead of starting with a whole bunch of features, generating a point cloud, then trying to make the point cloud dense by interpolating through it, we start in the opposite direction. What we do is we begin with a surface that's nice and smooth, it's fully connected, it has all the properties that you want geometrically, except it's probably the wrong one. And now what you do is you can look at the projection of that surface on the images, and it generates a set of silhouettes. So for example, if you just look on the right here on the bottom, you see two, and these, in fact, these are the reconstructions. So I'm kind of showing it to you backwards, but suppose you started with these two surfaces of the salt and pepper shakers. Now you can look at the projection of those on one of the camera images, and you can see where that surface would show up if you inserted it in the scene. How would you see it in the image? It's kind of like, you can think of a little bit about like virtual reality, how you insert an object into a scene. And you can see how well that silhouette aligns with the actual image itself. And if it's a good match, then your surface is probably a decent estimate of the true 3D surface. And if it's a bad match, then you need to fix your estimate of the surface. So from this, we can set up models where you postulate an initial 3D surface in space. You look at its projections in the image, and you measure how good those silhouettes are. And if they're good, great. If they're bad, what you need to do is figure out how to evolve the surface to make those silhouettes a better and better match to the image data. Now, I'm not going to get into the detailed mathematics of how you get that evolution, but the punchline is that it is a mathematically deterministic problem that you can solve. And what you get at the end of the day is a time evolution equation in the form of a partial differential equation that tells you how to continuously evolve the surface. So instead of jumping from one guess of the surface to a new guess, you actually continuously deform the surface, and the PDE that comes out of the mathematical analysis guarantees that that deformation will constantly improve the silhouette matching of the images themselves. So as the surface evolves, so do the silhouettes, and you get a better and better match. And when you run this process to completion, you converge to a better reconstruction of the scene. I'm going to show you a demo of this in just a couple of slides here. But let me just highlight now when this does and doesn't work, and how it actually fits into a certain niche set of applications, which are starting to become more and more important now. And so where it does not work is when you have surfaces that have a lot of sharp features, sharp point features, because these surfaces are, these models are based on certain smoothness assumptions that get violated in scenes that have a lot of corner features and singular texture points that stick out. Now, the good news is that's precisely where the traditional point cloud techniques work. Now, where this does work is precisely when you don't have a lot of point features, or when they're so incredibly dense that the feature matching problem becomes impossible. And that's the class of problems for which these mathematically driven approaches in computer vision for 3D reconstruction actually work quite well. So, let me just show you now kind of a visualization of how it works. Here's 4 images of that salt and pepper sequence that I was showing you before. So you have 4 images. And now what you do is you start off with an initial surface. You see the ellipsoid that I start off with on the left. I'm showing you below 2 of the silhouette projections. There's actually more, but these are 2 of them, so you can see how they evolve into the images. And now what you do is you evolve that surface by these partial differential equations, and you see that that evolution is chosen to make the silhouettes become better and better segmentations of the actual camera images themselves, and that induces this nice flow of the surface that allows it to pull out in a nice continuous deformation the structure of the salt and pepper shakers. And so I can show you an animation of it, and here's actually what happens. So you start off with the ellipsoid, and then as it evolves, now this evolution used to be very, very expensive several years ago. Now with GPUs and parallel processing, you can make this faster. And you can actually combine this with point cloud-based approaches if you can come up with kind of a crude initial guess. So rather than starting with something like an ellipsoid, you can start with something that's a little bit closer to the true surface, and then deform from that point on. So there are several ways you can speed these things up and make them practical now. And so now what you can see in this image is you can see the final segmentations that we get. You see now the silhouette superimposed on the actual data of the image itself. And you can see that we've got good agreement in 4 out of the 5 images. Now you notice in one of them that the agreement is actually off. And the reason is, and I haven't begun to talk about this now, but now's the point where I'm going to bring it in. There's another very important problem that you have to deal with in computer vision for 3D surface reconstruction. Other than getting images that allow you to capture features from different points of view, you need to be able, even for point feature-based approaches with point clouds, you need to be able to know accurately how those points in 3D space relate to points in the 2D image, and that requires that you know very accurately where the camera is situated in 3D space and in what direction it's pointing. So we call this the extrinsic camera calibration problem. There's an intrinsic part of it too, but typically those are solved in most modern day cameras. So trying to determine the camera pose, so where is it in 3D space, what direction is it pointing, is an important problem. And part of the reason why the accuracy of 3D reconstruction techniques using your cell phone are not where they need to be for most commercial applications is primarily due to the camera calibration problem. So what you see now in that 4th image is the effect of bad camera calibration. So 4 of these cameras were estimated very, very well in terms of their pose. Another one was miscalibrated. And you can see by the projection how bad the calibration is, because we've actually got more or less the right surface. And yet when we project it on the image, you see that it's off by many, many pixels, probably about 30 pixels. This type of camera miscalibration would actually be quite a disaster for point cloud-based approaches, because it would generate a whole bunch of points that would be still embedded within the point cloud generated from other points of view, but all of them wrong. And they wouldn't be obvious outliers to detect either. So one of the advantages of these PDE-based approaches is that you can directly impose certain types of smoothness assumptions in the evolution that give you this kind of robustness to camera miscalibration. Now, of course, it only works if only a few of the cameras are miscalibrated. If all of them were, then you'll get junk. And actually, I'll show you what happens in another image now. Just to show one more quick example, I showed you the example of one surface that as it evolves, split into 2 different objects, showing the flexibility that you don't even necessarily have to know how many objects are in the scene. Although if you do know, it's a good thing to exploit. You can go the other way around too. If you want to populate the scene with lots of different objects because you don't know where the true one is, you could imagine starting off with several different ellipsoids, and then as they evolve, they can actually merge together. And you can see that evolution process here. So I don't know where the object in the scene is, so instead of trying to put an ellipsoid where the object is, I put several. I could do more than two. The two just it shows the point. And as they evolve, they can merge together and little by little grow and carve out the object during the evolution process. And so here you can see the final 3D reconstruction. The reason that I've titled this slide "No Texture Mapping" is that in academic conferences, when you show the quality of a 3D reconstruction, if you texture map the actual image data on it, it hides little defects. So showing the reconstruction as just a shaded surface allows you to see all of the little details and see what defects are there and what defects are not. So it's typically expected in conferences that you show things without texture mapping so that you aren't suspected of trying to hide anything. So now let me touch on the calibration issue a little bit more now, and show what happens if you just have all of your images badly miscalibrated. Actually, not even badly, just a little bit miscalibrated. So here's another example of an object with almost no texture features that you can identify. So if you try to do a point cloud reconstruction on this, it'll be quite difficult. And even if you try to use a modern 3D stereo camera, it's going to have a hard time on this unless it can project a texture pattern on it. Just especially black is very, very difficult for infrared. On the other hand, it's precisely that lack of texture that allows you to segment this quite well. So here's an example of coming up with 8 camera images, all of which are miscalibrated. So what we did in this experiment, just to demonstrate the importance of calibration and why it's something that is a nuisance that has to be dealt with in any kind of commercial application, is we came up with the correct 3D reconstruction. We came up with the correct camera calibration, and then we just randomly perturbed the camera locations the correct ones. We randomly perturbed them by about 10 pixels. Actually more like 15. And each camera was perturbed in a different way, so they weren't done in a coordinated way. So all 8 of these cameras are off. Now, the reason that we're showing you the correct 3D reconstruction projected is so you can get a sense of the miscalibration that's involved here. Now, what happens if we apply the approach that I showed you without good calibration on any of the images at all? So if you do that, then you get this reconstruction. So here's 2 points of view of the same surface. We start off with the ellipsoid, we evolve it, and all you can see is this really coarse, noisy, rough outline of the horse. You can sort of see where the head is and the neck is and the body. You don't get the legs. So basically anything that's within about 15 pixels, you could sort of capture, but small details that you really need that 15 pixel accuracy for are all lost. Now, here's the nice thing is that, so here's just different points of view of the final reconstruction so you can see what it looks like. The good thing is that you can actually incorporate in these PDE techniques calibration refinement too. So you can, once you've kind of done the best that you can with bad calibration, you can evolve not only the surface, but the pose estimates of the camera together. So as one evolves, so does the other, and they feed back on each other. And here what you see is an evolution of the surface that's allowed to evolve together with the pose estimates of the camera. Now this is a little bit expensive, but it does make it difficult to do, if you have serious calibration errors. So I don't think we're quite yet where we need to be for real time if you wanted to use this type of an idea here for cell phones, but we might not be too far away from it in the next few years, especially as computational power gets better and better and better on cell phones. But the point is, you can fix some calibration errors even with these PDE techniques. And so I'll show you now a video. So here you can see oops, I went backwards, sorry. Here you can see an animation now of the whole process. So we'll first start with the ellipsoid and we evolve it with the bad calibration. And that's the answer that we get. And now we just rotate it around so you can kind of see this 3D effect. And now we do the coupled calibration, in other words, camera pose estimate and surface evolution all together, and we obtain this final shape here. All right, so let me move on. Here's really an acid test of these PDE-based evolution techniques, because one thing that's understood to be excruciatingly difficult to reconstruct with point cloud-based approaches is water, surface waves. This is a project that I was involved with a colleague who's an oceanographer, and they wanted to use 3D vision to do reconstructions of the surface waves outside of the Venice Canal as part of a rogue wave detection system, so that they could raise the barriers to protect the canal. Also, structural engineers are interested in the statistical distribution of waves at different frequencies in order to, determine the stress properties that are necessary for the material. And to do that, you need a nice, highly detailed reconstruction of the waves, so you can then do a frequency analysis afterwards and determine the distribution of power at different frequencies. So what you see here are two images. There's a left image and a right images of a tower that's overlooking the water, and the cameras are pointing down. And we do a 3D reconstruction. And so this involves estimating a height map, which you see on the left. This thing that looks like clouds, they're actually height values. So white is high, dark gray is low. And then we also estimate the texture, and then we put the two things together, and now we can get a reconstruction of the wave patch. So here you can see this from different points of view. So I'm just showing this here just to show that there are actually mathematically, sophisticated techniques that can handle even the challenging problem of reconstructing the shape of water, which is well known to people that work in surface reconstruction to be a difficult and challenging problem. Okay. So the last thing I'll talk about for a few minutes here is, how can we now incorporate these more mathematically based approaches to computer vision? I'll call them physically modeled based approaches. We actually have a model of the surface, the top-down approach. Can they also be combined with machine learning? Because point cloud-based approaches now can be combined very easily with neural networks and deep learning. We can also do similar things with the PDE approach too. And so this is just a quick demonstration of how you might do it. So here's an illustration of a challenging problem where you would really want to use some machine learning. So the idea is that you want to segment, you want to do character recognition, and you want to be able to detect the boundaries of handwritten fours. So what do? You take a database of different versions of handwritten fours, you train on them. And what we do is we develop a model of the shape that has a small number of degrees of freedom. So instead of evolving the shape where each point evolves independently of the other, you have a shape model that's trained on that maybe has 10, 12 degrees of freedom. So you can imagine an ellipse, right? An ellipse has a few degrees of freedom, right? You have the center point of the ellipse, you have the major axes, you have the rotation. Now that's an example of an analytically derived model of a shape, but you can also do that with a machine learning. Okay, so just to show now the power of this technique. So here's an example of a figure 4 that was not included in the database that we trained on. And what we do is we add some obstruction to the handwritten 4 by putting some vertical and horizontal lines in the background. Then we add a whole bunch of noise. So in the middle image now you see that's what we want to segment. Now this of course would be extremely challenging to segment with any kind of typical computer vision method if you didn't have some training involved. So now what you see in blue is an instantiation of the trained model, a wrong one. So the model depends on a small number of parameters. We choose the parameters randomly. That random choice of parameters, even though it's random, will still look like a 4 because that's the point of the machine learning, right? So Now we evolve those parameters, and as we evolve those parameters, we're always looking like a 4, but since the evolution is constrained in this highly coupled way, we evolve continuously from the wrong 4 that you see in blue to a better estimate of the actual handwritten 4, which you see in red. So it's still a nice continuous shape evolution process. It's a 2D example rather than a 3D example, but you can play the exact same trick in 3D. So here's just a quick explanation of how the process goes from beginning to the end. So you take a bunch of training shapes. So here's another example where I take, silhouettes, top-down kind of bird's eye views, silhouettes of airplanes, you generate silhouettes from them. Now you align them. You want to get rid of the pose, you want to center them as much as possible, rotate them so they're aligned, maybe rescale them so they all have the same area. You want to try to take the pose factor out because that'll be part of the estimation problem later. Now, once you've done that, you can, oops, sorry, I'm going the wrong way. Now there's a little bit of mathematics that you can do, that you can take these aligned shapes, you can subtract out the mean, and you can do various machine learning techniques. One of the most basic and historical ones is called principal component analysis. And when you're done, you come up with a model of the shape, which I'm showing in the bottom here, which is some average shape, which is this middle symbol, plus, sorry, a combination of some weights, that's going to be the parameter, times these learned modes, right? So when I said we start with a random set of parameters, that's these weights W, we evolve those weights, and that causes the shape to evolve. So here's an illustration of how that works. So what you see on the left here is a random surface, is not a random surface, is the average surface that we got from our training. And if you cut it to look at what the contour looks like through, you see this example of an average looking plane. And now here's an example of one of these modes that we learned during the shape process. And if you add that or subtract it, if you notice the surface in the bottom is just a flipped version of the surface in the top. So on the top, I'm adding it. On the bottom, I'm actually subtracting it. And as you see, as I do that, it changes the shape. In one case, when I add it, it pulls the wings in. In the other, it pushes them out. So I still look like a plane as I evolve. And so here's an example now that gives you a sense of what you've trained on and what you've learned. So what you see on the left, both for the example of the plane on top and the figure 4 on the bottom, is the average shape that you trained on. Then in blue, you see what the variation of the shape looks like around the primary mode of variation that you learned. Then in green, you see what it looks like plus or minus the second mode, plus the third mode, and you can do more than 3. This is just an illustration. And you can see that as you evolve and move along these modes, you still always look like a plane. You still always look like a 4. And so here's an example of applying those now to actually solve challenging segmentation, shape, detection problems based on combining PDEs with machine learning. So the last thing I'll mention here, and then I'll switch it back over to Kumar, is that you can apply this now on multiple images too. So for example, if you're trying to do 3D reconstruction and you want to try to track and segment a moving person or another object from several different points of view, you can see on the top the attempt of trying to use machine learning on an image by image basis. And you can see that on the last 3, the middle one and the 2 on the right, that it did a good job. But you can see 2 failure modes of the machine learning on the left, where I did not get a good segmentation of the person. But if you combine them all together, you can actually train on the quintuplet of images, so that as you evolve your estimate of 1, you're automatically coupling 2 into the estimate of the other 5. And it's a bit like what I showed you with top-down stereo, that you have a single 3D object, and as you evolve it, its silhouettes change accordingly in all of the images. And this is a similar concept at play here. So this is an example in 3D with multiple images, how you can apply machine learning together with PDE methods. So Kumar, if you want to go ahead and take over at this point. I think this is a clean point for us to switch.
Thanks, Tony, very much. And Chela, do you want to pause for a moment for any questions before I continue?
Yes, we can do that. And while we do that, we can also launch the last of the survey that or the poll that we wanted. Do you want to do that too, Kumar?
Yeah, I mean, I think it's we're done with the CV topic. You can still ask the, it's not a bad idea to get some answers for that. So please go ahead.
Sure. We launched the third poll. Also, we encourage all our audience to have any questions. They can start asking them in the control panel. The last of the poll was today, all walks of life are touched by CV. Let's see if you are an active or a passive CV user. You can select multiple answers here. So select all that applies to you. If you have multiple things that apply to you, you can select them. In 30 seconds, encourage all our participants to answer these poll questions. Great. Great. I think the results are in. So about 80% of the people said that they attend Zoom calls regularly, and 80% of the people also said that they're exposed to security cameras on the street or corner. About 50% of the people said that they use the facial recognition feature on the smartphone. About 10% are actively involved in computer vision projects.
Okay, hopefully we encourage the rest of you to start working on computer vision projects.
Yes.
Good, thanks for the poll, Chela. Let me share my screen and let me pick up from where Tony left.
Yes.
So let me know when you're able to see it.
Yes, we can. You can display settings, you can change that, and then it'll be set.
Yes, I'm going to do that. Is it better?
Great.
Okay, so one thing before we move from this computer vision topic, you might be wondering, is everything that Tony just talked about, is it possible on a mobile device, right? And like Tony, I think Tony mostly answered the question. He said the calibration, lack of good calibration is going to be a hindrance. And we have also tried a lot of different 3D reconstruction projects on mobile device. And one thing that we notice is the lack of accurate depth information is a challenge. And I know some devices are coming up with LiDAR, and that's going to help. But right now, that's a challenge. And there are some camera add-on products with depth sensors, but then for our use case, it's not practical for mass consumer adoption. Augmented reality that is been released both by iPhone and Android actually does use internally machine learning and computer vision, and it works very well. It's a great product for superimposing digital content on real scenes and creating nice game experiences and so forth. But in our experience, for accurate measurements where we are looking for within a couple of millimeters of accuracy, the technology is not ready yet, and that's primarily because of the same reason, which is the phones do not have a depth camera. So for now, our belief is that the best bet is to combine computer vision techniques with some kind of a machine learning technology if you are going to use a mobile device for body scan. And Chela, feel free to pause anytime if you have any question, but let me keep going. So with that said, let's discuss the couple of deep learning models on after you're done with the body measurement, what do you do, right? For the mobile scanning, I mentioned deep learning is a possibility. At the training time, if you want to measure somebody's feet, for example, getting data can be a challenge, and we'll talk about how you can use crowdsourcing with annotated data sets and how you can use synthetic data generation to augment the data. And there are also some considerations that you need to keep in mind as you deploy this model, whether the inference happens at the edge on the device itself or on the cloud. We'll talk about some of those things. And the second model that we use in this use case is actually incorporating the customer preferences, either expressed by the answers that they provide to some questions that you ask them, or by actually looking into the purchase transactions of the customers that measure with you. And the trained deep learning models can really use this information, combine that with measurements, and can be very accurate predictors of lasting purchases. Training how do you train these deep learning models? The first thing that we learn is get the data lined up. We'll talk about that more in a bit. Training and tuning requires expertise, human expertise, to do it right. Serving the model requires consideration of edge versus cloud. And finally, we'll touch upon the fact that just creating a model and deploying it once is only the beginning. You really need a very sustained learning, you need some kind of a workflow pipeline that you can feed new data and new changes to the parameters in to keep getting better and better models for the future. So in terms of getting the data itself, data is still the king. What we notice is that 80% of the time is actually spent on data, whether it is acquiring it or cleansing it, labeling it, or augmenting the data. Majority of the time is spent on data. And how do you acquire the data? There are several data set search engines on the internet. Google has its own, Kaggle is a well-known one, and there are search engines that are specific to the problem domain, like natural language processing has its own search engine. And then there are specific data sets, probably some of you are already familiar with MNIST, which is basically a database of handwritten digits, and its purpose is to train a model to recognize human handwritten text. And there are data sets for housing, and specifically for computer vision. ImageNet is a very popular data set. Google has its own open images. There are data sets that specifically give you sentiment analysis information, and we are all familiar with the self-driving data sets, right? We all know that Tesla is generating enormous amount of data based on actual at-road driving conditions. The right approach is to look for a data set if it's already available on the internet. It could save you a lot of time. But in our case, for example, for body measurements, what we found was finding data with real human scans was just not available on the internet on a ready-made basis. So, in those cases, what you do is you can turn to crowdsourcing. There are companies that would actually source this kind of data from real people for a small payment. And the good thing about this is it could be problem specific. It could be really tailored to the needs of the model. But even what we have noticed is even if you get crowdsourced data, it is not going to be enough to train a really robust model, deep learning model. And you might end up actually adding some synthetic data on top of it. For example, I'm showing here on the left a human foot. So what we did was, in order to generate this kind of a foot on different backgrounds, what we would do would be to manually annotate the body out of it, and then just replace the backgrounds with thousands and thousands of them. You can do the same thing for clothing. You can annotate, the rest of the image out, and then just have different colors of clothing and so forth. It was a struggle to actually synthetically generate human skin, which is somewhat complicated. But we could do the annotation for background, the synthetic data generation for the background and the clothing and so forth. And at the end of this process, whether you start from an internet-based data set or you are using crowdsourcing and augmenting it with synthetic data, you should eventually have a good amount of data for you to start the training with. And in case of model training, it's model training has been growing both faster and longer at the same time. Basically, that means that the models themselves are getting very complicated, and Moore's law, which is refers to doubling of the time it takes, has been holding true for model training thus far, at least. So you got to be cognizant of the duration of model training, which could be somewhat very expensive. So starting with the right amount of data and the right kind of data helps. One thing that we have noticed with data is that it's not the quantity, but it's the quality that matters. Identify bottlenecks and optimize. Make sure that your GPU, especially if the model is using GPUs, which increasingly most of them do today, make sure that the GPU utilization is consistently high, right? The lower the GPU, the longer it's going to take. The lower the GPU utilization, the longer it's going to take. Hyperparameter tuning requires human expertise. There are tools out there that do it automatically for you. I personally have not seen them work very well, but I'm sure that will be definitely in the future. And there are some tactical things that you can do, which is including, for example, misprecision training. So instead of constraining all the weights to be 32-bit floating point numbers, you might relax that restriction and have some weights, just be 16-bit floating point numbers, and that looks like that saves us a lot of time. So these are some of the best practices on the model training side. In terms of serving itself, you can either deploy it on the cloud, easier to code and deploy, but could be costly when the number of devices, edge devices, is very large. The cost could quickly, outrun your budget. And you could also potentially have some latency issues because you need to connect to the cloud. But then, in this world, every device is connected, right? So it's not a huge bottleneck in terms of connectivity, but it's probably going to be problem specific. Edge deployment is more responsive, obviously, because everything happens on the device, and it's less expensive because you're leveraging the processing power of the device itself. But what we have noticed is that the skill that is required to do it correctly, meaning mapping the data structures from the model to the device, the tools that the device provides, at inference time, could be a challenge, and that should be a consideration. And like I said before, training and deploying once is just the beginning, right? You need to have some kind of a pipeline like this because new data keeps coming in, and you're always tuning the parameters of the model to make it better. Some kind of a workflow that's ready to take all this new information and provide a better model is a must. We have learned that for experience. And you probably also want to have some kind of a model repository that can have version control, because you can soon run out of knowing what model has been deployed where, right? So you need to be some kind of version controlling and tracking is needed, and being ready to create a new model every time new data shows up is real key for sustained learning. And so just to sum it up, right, focus on the quality of the data, not the quantity. Train and tune carefully. Trained personnel are needed, especially if you want to do some of the things that I talked about, like edge-based inference and so forth. And invest in some kind of a workflow for sustained learning. So hopefully, this thing was educational, and Stella, hopefully we are a few minutes on close to time. So I will pause here, and Tony and I are ready to take any questions.
Great. Kumar, Tony, thank you very much. This was very excellent. And first of all, before this, I didn't know how complex this world is buying something simple as a shoe or a furnishing kind of a thing, or even a apparel, trying it out on things. So it was very, very educative, and thank you for that. We have quite a few questions. The first question is, I think I want to set the context here, Kumar. I think you talked about it briefly. The depth calculations on the current cameras are not good. So with that context, I think the question is, does the commonly available camera, such as the smartphone, better at doing the surface calculations as compared to the point cloud? Could you talk about it more?
In fact, I'm going to defer some of it to Tony, but one thing I will just mention is that lately, what we are seeing is there are cameras that are coming in the market that include the LiDAR technology, which stands, I think, for light detection and ranging. And with that depth information, I have some experimental evidence that we are able to get reasonably good 3D reconstructions. But in terms of, which one they would work better with, point cloud versus depth-based, Tony, do you have any thoughts on that?
So is the question the accuracy of the depth or the accuracy of the reconstructed surface? Because they are subtly two different things. Do you want me to just elaborate on both, or do you want to clarify?
Yeah, I think the question was with the smartphone technologies, right? So which is better to use it, or if there is anything, or should he be using both of them, is the question.
All right, so if the goal is to get a visualization of a 3D surface, a point cloud is really all that you need, because it depends on what you want to do with it, right? So in fact, you can use a Connect device, and current smartphones, have software in it that can generate. So if you just want to look at a 3D point cloud, your eyes do a very good job of understanding that representation in terms of matching a 3D surface to it. So, and in that case, the calibration problem doesn't matter, because if you're looking at a point cloud generated from one point of view, it depends a little bit on the sensing technology. So LiDAR actually directly measures depth. That's the actual raw measurement. Stereo depth cameras compute it internally from two different points of view. There's two camera lenses next to each other. They know the relative calibration of one to the other. And from that, they extract the point cloud using these feature detection techniques that I was talking a little bit about. They will sometimes struggle depending on the lighting conditions and the availability of texture. But apart from that, whether it's LiDAR or whether it's stereo depth, from one overall point of view, a point cloud representation just for visualization is fine. Now the question is, do you want to get measurements out of it? And for that, there's two nuisances that you have to deal with. One is it enough to get the depth, kind of the point cloud, from one point of view? So is what you want to measure something you can see from one point of view only? If so, then it's reasonable to approach the second set of nuisances, which is from that point cloud, you can generate a smooth surface. You can interpolate a surface across it, or you can try to identify certain semantically meaningful feature points from the surface, if you know what you're looking for, depending on what measurement you're trying to get. And for that, calibration can be a little bit sloppy because it's just from one point of view. And really the only thing that miscalibration is going to mess you up on is an overall scale. And there are ways of addressing that. Okay, so if you can get the geometry up to scale, right? So you can imagine that the camera's close versus the camera's far away, and the point cloud looks the same except one looks bigger than the other, right? So that's the scale issue. So resolving that scale is something that can be approached with, take a picture of a known object or of a known scale, compare that to the one that you constructed, and you can resolve it. Where the thing becomes, so that's the set of nuisances that can be addressed reasonably well. Where things get really complicated is when you have a geometry that you need to take measurements on, and you need more than one point of view because part of the geometry includes part of the other geometry. For example, with Kumar Atrix, we're trying to reconstruct the full geometry of the foot, and it's not enough to just have one point of view. You need to see the back of the foot, the front of the foot, the two side profiles, right? So, and now the problem becomes. And whether you do point clouds or these PDA techniques, the problem boils down to the same thing, except it has a different set of solutions. You've got to glue this information together, right? So now calibration becomes important. So it's not enough. It's not just a matter of scale anymore. So if you want to take the point cloud that's generated from one point of view and kind of merge it with the point cloud generated from another point of view, then that means you need to put those point clouds in a common reference system. And to do that, you need to know how one camera is situated with respect to the other camera. And that's where calibration becomes very, very important. So what I would say is right now it's solving the calibration problem with your smartphone in typical challenging environments, such as outdoors with glares and uncontrolled scenes, is a very tough problem. So if you can limit it to just resolving scale, which is something, and you can do that because you only need to do measurements from one point of view, then I think it's a problem that can be dealt with right now. If you need to glue multiple points of view together, we're not quite where we need to be, because the algorithms that do this require a lot of computational power. So if you're trying to do this in real time, it's not going to be very, it's typically not going to be amenable to real time. But more importantly, they also typically require a little bit of control on the scene conditions in which you acquire either the images or the point clouds. Does that answer your question, or did I kind of miss the?
I think it answered.
I kind of walked around it because I wasn't exactly sure what you're looking for, but hopefully I got it somewhere in there.
It's a nuanced answer, so I think that's probably. Yeah.
Thank you, Tony. The other one is a much more broader or a kind of a generic question. So the question is that are there any algorithmic bias either because of the synthetic data or otherwise, and how can we overcome some of those biases?
Cannot think of an algorithmic. By the way, the synthetic data itself is constructed very carefully, right? It's the way it is constructed, like I said, is if you want to replace the backgrounds, it's a manual. Today, at least, it's a manual task. You segment out the portions of the scene that you do not want, that you want to be preserved, and leave the rest of the background and just replace the background. So it's a manual process. It's got to be done very carefully. Like I said, it requires some. Like I kept repeating, right? Data, quantity, we've learned it the hard way. Quantity doesn't cut it. It's the quality that matters.
Right. Okay. There's another question here, which is about the model serving. The edge versus cloud deployment you talked about, Kumar, as the power of edge devices getting better, especially in the areas of specialized locations, could be the manufacturing factory or like autonomous mobile. Do you expect the edge deployments to increase in adoption and deployment of these things?
Edge is the future, right? Right now, we are going to the cloud only because for two reasons, to be honest with you. One is we don't have the skills to actually do the edge model inference correctly. It's a challenge. It can be overcome very easily. It's just that a lot of people do not have the time or investment in that, and that's one reason. And cloud is a lot easier to code option. And secondly, to the point of the person that asked the question, the edge devices, and also Tony made this point earlier, in terms of the computational power, they're not there yet. But like Tony said, computational power of the edge devices is only going to improve. And the models are going to get more complicated also, but that notwithstanding, I still think edge devices is the future. Edge computation is the future.
Great, thank you. I think this is again kind of a follow between the cloud and our semi non-cloud kind of a question. With the question is that there's a lot of personal data that is being captured using CV, computer vision. Are there security concerns in that context? Which is a better option? Should it be on a cloud or should it be in any other, like on-prem or a private entity?
If you just pose it as a security question. Obviously, doing everything on the edge is more secure, right? You're not even sending any data over the network to the cloud. But even if you're doing everything on the cloud, for example, we have apps that have customers use a smartphone to take a picture of the foot. And what we do is, and like Tony said, without a reference object, it's impossible for us to measure, to understand the scale, right? Whether the phone is situated 5 feet from the foot or 7 feet from the foot makes a lot of difference. So in order for us to address the scaling problem, we ask the customer to place a credit card sized object on the floor, which kind of gives us the reference point. And one thing that we do, for example, is the credit card itself is completely masked even before it leaves the device and goes to the cloud. So that's one example of how security considerations are addressed. So yes, the caller is right. Edge is always more secure, but you can address the security issues. You make sure that you send it on a secure protocol, HTTPS, the data, and on the server side, we make sure that nothing gets stored on the server for a period, right? And if there is some sensitive information like credit card, we mask it. So those are some precautions that you can take even if you do it on the cloud.
Okay, great. Here's another question, which is around the same thing, around security and other stuff. Can humans deliberately cheat or manipulate the CV technology or the algorithmic technology that is being talked about here? Can there be any way, can somebody knowing this, can they alter this outcome?
I mean, all they are being asked to do is to present their body to a scanner or to a mobile device. So if the person is asking about, a man in the middle attack or something like that, where somebody, I think the same cloud considerations for security should apply here also. There's nothing specific about this computer vision problem that makes it more vulnerable to security attacks.
Okay. Great. We'll give a couple minutes if there's anybody else who's asking any other questions. I don't see anything coming up. Otherwise, great. Thank you, Kumar. Thank you, Tony. It was a pleasurable conversation and hearing from both very mathematical, computational approach and a pragmatic approach from Kumar's point of view of using the technology to something that is usable in the hands of people. I think it's amazing to hear from both of you and the path that is taken in right now. It's great. Thank you very much for your time. And that concludes our webinar for the day. Thank you.
Thank you all.
Okay. Thank you, everybody.